one of the things I think is really cool about this is Chandler sort of he embodies the young, the new generation. So he owns Clang at Google, and he's going to come out here and teach us about Clang. I don't know, most of you have probably used it, maybe not, but come on out here, Chandler.
All right, so I'm here today to talk to you a little bit about Clang. I want to thank Herb and Charles for actually inviting me to come talk to you about Clang. It's a really great opportunity. It's a great opportunity to get to talk to a lot of people who may not be exposed to Clang in kind of their day-to-day interactions with C++. Just as kind of, just to get a feel for things, how many folks here have ever used Clang? Like even once? All right. How many folks here have used Clang in the last month? How many folks here use Clang because of this talk? All right, some of you aren't being honest. Okay, that's okay. So Clang is really interesting, and because it's very new and because it doesn't support as many platforms, it's still gaining a lot of traction. I want to try and give you guys some background on what Clang is, where it's come from. So let's talk a little bit just very generally about Clang. Now, the first thing I really want to talk about Clang is where this came from. Why did we set out to build another C++ compiler? We have quite a few C++ compilers out there. Why are we building another one? And this isn't an easy task either, right? Why did we choose to do that? And to understand that, you have to understand the C++ compiler that a lot of people in the world were dealing with. It wasn't nearly as nice to interact with as Microsoft's Visual C++ compiler. I wish that it were. And you could tell this because you would write code, and you would make some mistakes. You would leave out some curly braces. You'd add some in the wrong places. And you would compile your code, and you would get something that looks like this. Now, I don't know about you, but having tokens listed does not help me correct my code. All right, this is not useful, right? And that was just the beginning of the problems that we have with the existing open source compilers, right? Because it's also pretty slow, and it's no fun to sit around waiting for your compiles to finish, right? This is not what we want out of our compiler, right? And then we get to the really fundamental thing we want from our compiler that we just do not have in the open source world. Because what we want from our compiler is we want tools from our compiler. The compiler is a beautiful tool, but it is not the only tool. We need more than just a compiler. But we don't want to rewrite the understanding of C++ every time we write a tool. We want to use the same understanding. And this is a common theme. You can see it in any IDE. You can see it in any tool that's really helping developers with C++. But when you go and you ask, if you go and, as someone did, and this is a real quote from the GCC mailing list, by the way. I'm not putting words in anyone's mouths here. If you go and ask, why can't we take GCC's front end and use it? Use it as a library. Use it to build developer tools. You'll get a response that is not useful. One of the main goals for GCC is to prevent any parts of it from being used together with non-free software. Thus, we have deliberately avoided many things that might possibly have the effect of facilitating such usage. That is a direct quote from Richard Stallman on the GCC mailing list. Now, this is not a useful answer. This is a political answer, this is a social answer, and is not a useful answer, and we cannot build our tools with this. This does not work, okay? This makes absolutely no sense. What are we even doing with this compile? Okay, so we need something better. All right, so of course, we're not going to sit on our hands. So we tried to build C++ tools, and we tried to build them with GCC. We tried very hard. But very early on, we ran into code that looks like this. This isn't even C++. This is C. This is bad C code. And we just tried to build a simple tool to deal with this. And we asked GCC to analyze this source code, to tell us about it, to tell us how it worked. And GCC told us that it worked like this. We gave it this source code, and GCC came back. It's like, yeah, you gave us this source code. That's not the same thing, right? Do you see? This is not the same source code. GCC thinks it is. The parser inside of GCC, the parser does trivial constant folding. When it sees +0, it throws the tokens on the floor and keeps going. There's no AST, there's no semantic model for this. You can't figure out what has happened here. This makes implementing even the most trivial of C++ tools impossible with GCC. It's not suited to the task. So we needed something better. We needed something much better. Because given this response, what are we to do? Like if you lie to me about what my code says, I can't use this. You are making it far too easy to point the gun at my foot. You're practically pulling the trigger for me. I can't stand this type of manipulation of the C++ code. It doesn't work, okay? So we need something better. Fortunately, there is a group that was running into this called the LLVM community, a wonderful group that Chris Latner built and has continued to build at Apple, and they were hitting all of these problems. And they wanted to find a solution as well. And Chris Latner, in I think the truest spirit of open source, said, I know how to solve this problem. I'll write a new one. Right? We can solve this through code, right? And so we've got Clang. This is where Clang came from. It came purely motivated out of frustration and inability to accomplish the goals of anyone trying to support real C++ development, all right? And this is how we get Clang. Now, just to give you a background on where Clang is today, all right? Let's talk about the state of this compiler. Okay, the state of Clang is that it is a fully functioning C++ 98 compiler. It works. We believe it to be essentially as correct as we would like it to be. It's relatively bug-free. We're very happy with it, right? It's as bug-free as any compiler that's as young as it is going to be, right? We're very happy with it for C++ 98. It works very well on Linux. It works very, very well on Macintosh. It doesn't work so well on Windows, I'm very sorry. We'll get to that later. But it's a good compiler. We're happy with it. It's been the latest release was a very good release for C++ 98 code. Now, that's the current state, right? That's where we are. It's factored. It's libraries. We can build tools on it. We're actively building tools on it. But let's also think about what's coming next, because we've got some nice breaking news here. We've got some important developments with Clang. Clang is much further along with C++ 11 than a lot of people expected. All right, and this was very surprising to me, actually, and I'm actually one of the developers. And when I started really assessing it, the number of things that are missing in Clang is very small. We are missing initializer lists. We are missing the last few pieces of constant expressions. We're missing lambdas. We're missing, we're missing a couple of other things. We're missing unrestricted unions. We're missing a couple, like very few things. Now, they're important ones. The really fun thing is that I believe the list of really big and important things that are going to be missing from the next release of Clang is likely, no promises, but likely to be unrestricted unions, inheriting constructors, and atomic support, concurrency support. Concurrency support is something we're all learning. We're going to have the rudimentary atomic support, but it's very rudimentary. This is something we're going to be working on for a long time to come. There'll be some other smaller features missing, but we're actually going to have a generally complete thing. We expect to have constant expressions, initializer lists, and lambdas in the next version of Clang. So it's really, really, really close to the edge of C++ support. All right, we're really, really happy with this. Now, but keep in mind, I said maybe. And also, there are going to be bugs, because these features are very new, and they're very large. And one of the interesting things about Clang is that as an open source compiler, we are going to launch very early, right? You're going to see features very, very early on. You're going to see them when they're a little bit rough, and we're going to keep working on them. Now, we need to also talk about something a little bit different, though, because that's the history and the background on Clang. Now you know where Clang is. But I also need to tell you about a problem that we're facing today. An ongoing problem. This isn't just the problem that led to Clang. And it's one of the biggest problems that Google has faced, and one of the bigger problems that a lot of other companies have faced with C++. And this is what we're going to talk about for the rest of this lecture. And that problem has to do with Murphy. So we're going to talk about Murphy, and we're going to hope sincerely that he's not paying too much close attention for at least the next hour. So Murphy's law is very, very prominent in programming, right? Things go wrong. We all know this. But you need to understand the depth to which things can go wrong when you're working with a language like C++. If you're not careful, if you don't have all of the safety mechanisms in place, things can go very wrong. Because Murphy is not passive in this, right? Murphy is not a passive player here. He is actively seeking out the flaws in your code. Murphy is an angry, angry dude, all right? For reference, this is like a UK television series. I know nothing about it, but apparently it's got an angry Murphy, and that's what I like, because Murphy can sneak up on you if you're not paying attention. And when Murphy sneaks up on you, the consequences are not mild, they're not small, they're disastrous, okay? So we need to be very, very attentive when we're actually defending against Murphy. We need to be very careful when we're trying to make our languages safe, right? So throughout this talk, when I'm talking about Murphy, when I'm talking about things, I really want you to keep in mind, right? Like, you know, an angry, angry Murphy looking to cause a massive disaster. That's what we're trying to avoid here, okay? So with that perspective, there's one other element that really impacts the type of problems we see with C++. C++ is actually a very safe language. It's very safe. In fact, if all we had to worry about was like one programmer working in C++ and worrying about, you know, angry Murphy and the disasters that can come from that, I would actually be very happy. But the problem is we don't have one. We have a lot more than one. We have lots and lots of programmers all sitting around hammering away at keyboards constantly. And that means that the chances of something going wrong go up. And we need to take a lot of extra steps to try and fight against that. And one other thing I do want to mention, sorry, I have this disaster slide. I don't necessarily mean like fighter jets. I don't mean oil rigs. The disaster could be missing a ship date, right? The disaster could be purely in terms of developer productivity. It could be in terms of, you know, developers understanding the source code. But it could actually still be disastrous if it's a pervasive problem, okay? And this is something that's very, very important because we have a lot of developers and they're all struggling against fairly simple and small problems that we need to help them out with wherever we can, okay? And this becomes even more relevant as the number of developers magnifies, right? As you grow the number of code monkeys you have access to, all of them are collaborating, and you get a herd of monkeys, all of them trying to find correct C++. So we need to help out the code monkey some. And the way that we've found to do that with Clang is pretty interesting because it's actually taking it back. We actually kind of went back to our basics. So let's talk about diagnostics. All right, let's talk about diagnosing bad C++ code, all right? So this is some bad C++ code. It's pretty obvious what's wrong with this if you know what you're looking for here. But if you're typing fast, if you're working, if you're in a hurry, you can miss it. Maybe you miss it the first time. The important thing is understanding what's gone wrong when you miss it, when it gets into your program, and your compile fails. And Clang helps with that. Because with Clang, what you get is a very detailed explanation of what's going on. And now I'm going to take a minute to actually explain the structure of Clang's diagnostics, right? The first thing you're going to see is an error message, right? Clang's trying to say, okay, here is what has gone wrong. Here is what makes this program an invalid program. You've declared an array, and it has a negative size. And then Clang is going to start giving you extra information, okay? So it's shown you the array, right? It's shown you the array and the invalid size. It's underlining everything. It's highlighting exactly what's going on there. But we actually don't understand this, because what is in? Why is that negative? We need more information, right? Okay, so it says that it's in an instantiation. It tells you exactly what instantiation. It's in an instantiation of a class, right? And it's going to tell you what n is. N is 4 here. Okay, now I'm starting to understand why something has gone horribly wrong with my program. I meant 42, not 4, clearly, my bad, right? So we're starting to slowly break down exactly what's gone wrong. And Clang is going to step back through every layer of the templates with you. All right? It's going to walk up the stack, show you how your code actually ended up invalid. And this is incredibly powerful, okay? It's incredibly, incredibly powerful. Now, if you think that's amazing for templates, macros are much more frustrating. And as much as I would really, I join Herb in hoping that there is a world without macros. We don't live in that world. And unfortunately, we use libraries that were not written in that world. And those libraries impose upon us macros. We don't even know that they're macros half the time we end up using them. And so we need help. We need help understanding the macros as well. Now, the nice thing is that Clang provides the same type of contextual information when diagnosing errors out of macros. It's going to show you the error, but it's going to show you exactly how it formed that error textually in the preprocessor. Clang is walking back through each layer of the macro expansion, showing you what the next step is and exactly where in that next step that erroneous piece of code lived. So we can even see that, we know that it's this middle argument to the macro that's bad. We know that that middle argument is used in another layer of macro expansion, and we can show exactly what it got expanded into at the final stage. This is incredibly powerful for understanding exactly how bad code got into your code, right? You didn't write it, you wrote M2, but Clang can actually show you what happened, and that's very, very powerful. Now, then we get into less powerful things and more immediately gratifying things, because sometimes I'm actually a particularly bad person here. We're working really fast and we're not paying a lot of attention, and we have typos. Typos are the bane of programmers, but we have amazing tools to deal with typos in Clang, because we see that there's a base type here. Now, this one's tricky. I want you to look really carefully. There are two base types in this code. One of them's a variable. One of them's a type. Which one were we aiming for? Well, Clang knows that we can't be aiming for a variable. It's a static variable. You can't use a static variable in a member initializer, and so it knows certainly that you meant to actually name the type. And it tells you that you meant to name the type, and in fact it continues parsing the rest of the file as if you had named the type, so that all of the other error messages are just as accurate. All right, and it's going to show you how to fix your code, exactly where it got this type from, everything you need to understand exactly how to fix this bug. It's amazingly useful, okay? And Clang's very clever. It will even edit your source code for you in order to rewrite this if you would like it to. But it waits for your request. It's not going to do that just arbitrarily. So sometimes we make more annoying typos like this one, right? Because here we haven't just made a typo, we've also forgotten about a namespace. There are a bunch of other things going on here. Who knows where this code came from? Well, Clang does. So first, Clang's going to realize that you named a namespace without the right qualifier. Okay, we can fix that. We'll go and add a qualifier to it. But remember, when we add something to it, when we correct a piece of code, we recover as if that were what was written. Which means that we go down and we find foobar as well, and we notice that you misspelled that, and so we can correct that one just as easily. And we can keep going, and we can keep diagnosing errors in your source code without ever losing track of exactly what's going on. This is incredibly powerful, all right? This changes how you read diagnostics. This actually allows you to not send all of your error messages into head and just look at the first line, because you're going to continue to get accurate and useful error messages throughout the file. Now, just because Andre mentioned Oscar Wilde, I had to, oh no, I've got more. No, where's Oscar Wilde? We'll come back to that, okay. I think I tried his Oscar Wilde diagnostic, and the book is very small. We'll have that later, okay. So, now we're going to talk about something different. Now we're going to talk about things that aren't ill-formed. This is valid C++ code. Right? This code's correct as far as I can tell, right? Except there is certainly a bug in here. It's valid, but it doesn't behave the way we want. We've made a very simple typo in trying to use an old, crufty C interface. This is why C interfaces are bad. They're easy to make these mistakes on. Fortunately, there's Oscar Wilde. Sorry, my slides are betraying me. Bear with me. So Oscar Wilde, let's make sure we cover Andre's Oscar Wilde diagnostic. Because he had a legitimate concern. What happens when you do template expansions and they don't simultaneously, two template parameter pack expansions simultaneously, and they don't line up? It's a very complex piece of code. If it goes wrong, you can see screens full of error messages, or you can have the compiler tell you exactly what happened, because you had two instead of three. I told you that this one was worth putting in. Sorry, I did this at the very last minute because of his presentation. All right, so we're not done talking about diagnostics, don't worry. All right, so when you write this bad C code, Clang is going to help you out here. Clang is going to give you a diagnostic that is not an error message, it's going to give you warnings. We love warnings in Clang. This is the bread and butter of Clang diagnostics, are warnings. Warnings about incorrect code. Now, this is not invalid code. It's an important distinction. The C++ standard allows you to write this code, and it says exactly what it will do. But we can look at the code, we can look at the context of the code, and we can be completely certain that you did not mean to write it. There is no chance that you meant to take size of s here, because s has a completely different size. It's a pointer, all right? You're trying to set the contents of the pointer. We need to actually understand the context for that, but we have that in the compiler. And so we can tell you that you've used the wrong expression inside of the size of, and we can tell you how to fix it. It's very, very, very useful. This warning caught bugs in Chrome, an open source web browser that you might be familiar with. It found bugs in all kinds of code that we've pointed it at, because it's such an easy mistake to make, and very often things happen to mostly work. All right? And that's the most frightening part, is that oftentimes it will mostly work. It will initialize some of your data, just not all of it. And it can be hard to figure out why, okay? So then we can write more simple things, right? These are things that you might just write day to day, but unfortunately, even though this, clearly the user has messed up here. Something has gone wrong, and yet it's valid C++. Nothing says we can't actually write this code. Nothing says this isn't valid, but Clang is very certain you didn't mean to. And so it tells you that you've got an expression that's completely useless and that you haven't even returned from the function. It's trying to help you out here by looking at the semantics of the code, looking at the overall program meaning. All right, we can keep going here. There are so many places where clearly the user did not mean to write this 100 here. That's not okay. They can't just return that integer. There isn't even an integer there. They meant to write something else, right? And we can tell them that, yes, this is out of bounds. Actually, you have to write 99 there. You can't write 100 there. It's very, very important. We can even look at things that are a little bit more complex, right? We can look at things where clearly, maybe the user forgets to ever initialize x. Some of the time, Clang can actually detect this, right? It's trivial to prove to a compiler, although perhaps not to a human, that in fact you never initialized x. You never came close to initializing x. We'll tell you about that. We'll tell you where you used it. We'll tell you how to, make the compiler be quiet if you didn't care. I don't know why you wouldn't care, but okay. Right, we're trying to actually understand the program semantics and help you out. Now this one is actually one of my personal favorites, because I wrote this code. All right, I wrote this code. I thought it was correct. Several other people looked at this code. They thought it was correct. I mean, not exactly this code, but equivalent code, because it looks fine, right? We've been really careful to use a really big portable integer type. I know it's not standard, but we're getting that fixed. Yeah, it is now, thankfully, right? But we wrote a big type. We have space for this big number, right? We need 8 gigs of space here. What could possibly go wrong? Well, C++'s integer arithmetic rules are strange. They are not what you thought they were, and so this does something very surprising. This actually can, order you a burrito if it likes. And there's nothing you can do about it, right? Because this has no meaning according to C++, and that's very unfortunate. It has a little bit of meaning. But Clang is going to tell you exactly what's going on here with as much detail and precision as it can. It tells you what value you're trying to form, how many bits it needed, how many bits it had, where it all went awry. It doesn't matter what you're storing the value into. You have to actually compute the right value first, okay? Really important thing, right? This is a real bug, right? All the things I'm showing you are real bugs that actually got into real production software. These are things that are important to find, and it's very hard for a human being looking at this looks fine, okay? It's really hard to spot these errors through simple human review, so it's important to have some semantic checking here. So let's take it up another level. This is actually my favorite typo that I've ever seen in code, because this code looks beautiful. What's possibly wrong with this? How many folks have spotted what's wrong? Got a few people who spotted what's wrong? This code lasted for years. Years, okay? People didn't understand what was wrong with it. The question you have to ask yourself is, how many variables have you, how many things have you declared here? 2. That's a function, not a call. You've declared a function. There was a comma instead of a semicolon. Clang's not only going to tell you that you accidentally declared a function in a very strange way, it's going to see that you declared a function, there was a comma before it, and that was actually a function we could have called. It'll go look. It'll see if it was a function we could have called, make sure that we could call it, and then it'll say, oh, okay, you just meant to have a semicolon instead of a comma. We understand, right? It really, really works hard to clarify what the meaning of the source code is, to tell you how to fix your source code. This is incredibly useful. There are very few programmers who are going to look at this and understand why this compiles cleanly and yet does not call bar. All right? That is very hard to understand. Fortunately, we have a compiler. It can help. Okay. So let's get to even more interesting things from my perspective. Again, I want to reiterate, some of these may look trivial. I've made them fit onto a slide. These all came from real code. Real bugs that were live in the wild in production. Okay, so, maybe we're trying to check on a customer's state. We're like updating state. We're trying to make sure we know whether or not to charge the customer money. This is important here, right? Remember the burning things? Charging money is kind of burning things for companies, right? You don't want to do that the wrong way. Unfortunately, we have failed miserably at that goal. Because this doesn't actually set the flag to not charge people. No, it sets a pointer to null. This surprised many engineers that I talked to. This is setting a point. Where is null in this source code? I would have people challenge me. There's no null here. All right, this is one of the reasons why null pointer, why all of these new features in C++ are important to use. We have to move away from pointers, from this very sloppy and easily errored code. And Clang is trying to help you catch it in existing code wherever it can. So then we get to some other very, very interesting pieces of code, such as this. This is perhaps one of the most famous typos of all time. All right, this is so famous. Not only does Clang, GCC diagnoses it too. There are a whole category of errors around this, and we've tried to make as many compilers as we can gang up on them because they're so common. I have never seen a classroom of students learning C++ where at least a quarter of them didn't make this mistake in the first month. All right, it's just too easy. But fortunately, we have compilers that can help us. They're going to tell you, okay, hold on. You're assigning in a condition. That's not that likely. Let's actually take a closer look. We insist on a source transformation. Now, this gets to an interesting idea. What do you do when the compiler is warning you about code and you actually meant it? You actually needed to do exactly what you wrote, and we can't take that expressivity of the language away. That would harm the language, that would harm programs. Instead, we add extra syntax to make it explicit to the compiler that this was intentional. Syntax that you would never just, accidentally add to your program. If you wrap extra parentheses, completely pointless extra parentheses around this, the compiler's like, okay, I'll leave you alone, right? You get what you asked for, right? And so we have this ability to kind of silence warnings about questionable or bug-prone patterns by source changes, compatible source changes. And this is what's used whenever we get to warnings that are about bug-prone patterns as opposed to certain bug patterns, right? Because some of these, there's no question. We've never seen a case where the user intended it that way. But this one is questionable. So we need to have an escape hatch for users. Now, one of the interesting things, GCC implements this the exact same way as Clang does, by the way. But one of the interesting things we found was that we had failed to actually check for the reverse problem. Because sometimes people wrote the following. And they did not mean to write the following. They had been indoctrinated by this pattern of adding extra parentheses to use an assignment, and then they had made the inverse typo. And we didn't have any way to tell them about that fact. And so now Clang actually checks for that, and it says no. We've kind of blessed this particular syntax to mean assignment. We're going to enforce that. We're going to make sure you're actually doing it one way or the other. Now, this was not the only place where we need kind of compatible source changes to clarify code. This is something that I actually found somewhat surprising. I've talked to a lot of people who worked with C++. They found it surprising as well. This code is incredibly prone to bugs. And it's surprising that it is. People don't realize that these logical operations actually obey a particular algebra. They have precedence rules that follow from that algebra. That's not how they're thinking. And so they continually mistake what precedence relationships hold. And you get code written like this that was not intended to behave like this at all. And so in Clang, we actually have implemented a rule that we just don't allow you to do this. We warn on any implicit precedence relations between logical or and logical and we force you to explicitly group them so that we're certain what relations you want. And it gives you a very nice error message describing the problem and why you might be surprised by it, what the natural correction is, and you can go and add other parentheses as necessary. But we ask you to explicitly group them because it's so frequently bug prone. Now, another one, and this one was very surprising, this is another operator which has very clear precedence rules, and yet no one understands. So any guesses on what this function returns? X. Always X. Never anything other than X. That was very surprising to a large number of engineers. The fact that that plus would actually kick in, and of course we have a lot of conversions to bool. It's very easy to compare things for true or false, and so the cascade of errors just propagated. This became very, very prominent, especially with streaming output operators. Right? When you're writing to cout or cerr, those also group in a strange and surprising way, and they also have reasonably well-defined semantics when they're integers on both sides, and they also usually produce either true or false. And that's very, very surprising for users. And so this was very important for us to fix. Turned out it was very, very common in code. And then we got to something that I actually particularly like. This is kind of a stunning typo. And you can also, it's also hard because the indentation makes you really want it to be correct. Like the seductiveness of Python's indentation just knows no bounds, right? And so you look at this and you know what this should do, but fortunately Clang tells you what it actually does. It doesn't do what you want at all. All right, and then we can keep going here. There's so many cases here. You know, perhaps you're using a switch statement. One of the things we found was that switching over enums is very, very bug prone, but we can fix this in the compilers by warning about it. We can actually come up with a really systematic way to handle every single case. Right? Every single case, because this one's missing Z. We don't handle Z here. What happens when Z comes in? We just, you know, we don't get anything useful. And this is particularly important for maintenance, right? Imagine you have an enum. Maybe it's a very widely used enum, and you want to add something to it. How do you find every single user's code that needs to handle that new value? Right? Where do you even look? Right? We can actually come up with a way to write switches that are explicitly required to list everyone, unless you have a default case, right? Unless you have a default case, we're actually going to insist that you enumerate all of the enumerators, and that's very, very useful.
Got the break statement.
It's already buggy, man. How much more do you want, okay? Every single example of code I have is buggy in more than one way, apparently. So, all right. So then we can get to I think, even more interesting things. And so now we've got some strange patterns here. We've got a constant. Maybe it wasn't a constant always. Now it is a constant. But it turns out that we've ended up with, you know, dead code. Now that's okay. This happens sometimes. The common case is, you know, configuring your compilation. You can imagine that you want to enable some things, turn off other features, in debug, various other flag type values. You don't want to handle them special. You don't want to use more macros and more preprocessor tricks, so you just use the value and you write natural code. Unfortunately, these flags often guard invalid code or surprising code or incorrect code, code that would only be correct if the value weren't true, right? And so here we have such a case, right? When n is too large, we have an explicit return. We make sure that things don't break. So it's really, really nice that when we look at this, right? When we look at this, we actually see that 44 is past the bounds because it's a constant. Even though we seem to be handling things, we actually are trying to encode all the semantics here as closely as we can, okay? All right. So let's talk about static analysis, because we're getting into static analysis. All of these diagnostics, they're trying to reason about the meaning of your source code. We're getting more and more complex. We need to be honest about what we're doing. We're doing full-blown static analysis during your compilation to give you diagnostics about what is wrong with the behavior of your program. It's a key concept, the behavior of your program. And so as we get more and more advanced in that, and Clang isn't just your normal static analysis, right? Clang is it's a little bit more powerful than that. It's going to actually try and fight you over your bad code. And we're going to try and actually find ways to pin down even very subtle problems in your code. All right? Now this is a lot more code than I've been using. All right? This is when static analysis becomes important, when we start to have complex structures in source code. Now I've deleted a lot of code from this. You can imagine this would be a very large routine, it'd be a very complex routine. But there are subtle problems here. There are problems that may not be easily spotted during code review. There are relationships, there are preconditions, there are important constraints on the correct behavior of this code that are not being followed. We have mutual exclusion in play here. We're expecting concurrent access to this function. We have shared state in the form of a global variable, right? And we have some preconditions which are not being followed here. So there's at least one precondition that is trivially not being followed here. We are not correctly locking and unlocking our mutex. But what you don't see is that there are more preconditions that aren't even visible in the source code right now. In order to have compilers that are able to really diagnose the full range of subtle issues that come from concurrent programming, we need to give the compiler more information. We need to extend the language to give it specific domain information that will allow it to tell us about our code. And we can do this using C++11's generalized attributes to actually annotate the source code with critical information about its expected behavior. All right? Now I'm filling in kind of a dummy mutex implementation up here at the top, but you would imagine that your standard library would come with a correct mutex implementation with a full set of annotations that completely describe its behavior. And what you're really concerned with are these annotations such as guarded by and exclusive locks required. All right? These are the important annotations. They're on your code, and they're actually specifying the requirements of your code, not the requirements of of the library. And that's a very, very powerful thing. Because now when we look through this function, when we compile this function, Clang can do very detailed analysis of whether or not you strictly follow, in all cases, the requirements you've laid out through annotations. All right? Now, of course, I have to be fair and honest. I can't implement this today because generalized attributes are one of the things that's still about halfway in development in Clang. Sorry. I use the old attribute syntax. But I promise, it will work like this. This is what we want you to write. We never want you to see these. There are too many underscores. It's all bad, okay? This is what we want you to write. And the result is going to look like this. The result is going to be Clang going through and analyzing each step of your program and highlighting all of the missed preconditions here, right? We are reading a variable that requires locking without holding the lock. We are calling a function that requires a lock without holding that lock. We fail to lock that mutex across a loop continuation, okay? And we fail to unlock the mutex as we exit the function. All of this is clearly diagnosed by Clang. It's going to try and very specifically highlight what has gone wrong in this desired semantics of the program. Right? Now this is complex. This is a very subtle thing, right? And the importance of this is not for average code. The importance of this is for subtle code, for concurrent code, for code where it really, really matters. Right? And the way we get this kind of powerful checking of our source code is by extending the language. Every time we can extend the language to codify the semantics, we can actually get improved checking from our tools and especially our compilers. All right. So let's talk about dynamic analysis briefly. Right, let's talk about dynamic analysis, because static analysis is very powerful. It allows us to kind of set up invariants about our program and then enforce them strictly. Regardless of what particular execution takes place, those invariants are going to be held on all paths. But there's another type of analysis which is looking for something slightly different. It's looking for invariants that we may not be able to enforce pedantically throughout the entire code, but invariants that may be very important. All right? And dynamic analysis is a fantastic tool for doing this. So you can imagine you've written some code, some fairly poor code here, and you've written 2 bugs in this code. Now one of these bugs we can spot statically. All right, we can spot one of them statically very easily. Another bug, it's a little trickier. We might be able to spot it statically, but we're going to have to actually do loop trip count. We're actually going to have to look at that type of information, make sure we understand how it works. Even if we do manage to spot that one statically, you can trivially modify this. You can move things around and very easily end up being unable to actually spot this bug statically. So we would like to have HAL actually kind of, take a much closer look at the execution of the program and see if our invariants and if our basic correctness failed. And Valgrind is kind of the canonical tool for this, which is not related to Clang at all, but I'm setting the stage, so bear with me. So Valgrind is a canonical tool for this. You can see it will go through, it will instrument the execution, right? And it will tell you about the things that have gone wrong. You've used something that is uninitialized, and you've read past the end of the array. It's got a very good analysis of exactly what's going on. One of the downsides to Valgrind is that it actually catches a lot of other things that are irrelevant. It actually has a lot more text there, but I tried to distill what we're looking for. This is what we want. Right, but Valgrind has some problems, and they're very, very deep-seated problems. The first problem is that Valgrind cannot possibly instrument everything. In fact, if we change this code very trivially, we actually simplify the code here, right? This code is now less complex, and yet when we run it with Valgrind, we catch fewer bugs. All right? And this is a very big problem, because usually we're telling people to simplify their code. Right? You don't add complexity to your code to catch bugs. You simplify it to catch bugs. But as we simplify our code, Valgrind ceases to be able to analyze it effectively. And this problem stems from an underlying issue with Valgrind in that it's doing dynamic instrumentation of your executable, and it's doing so through very expensive means, right? Because it's actually simulating the execution of your program, and it's very, very costly. In order for that to be even tractable, it has to give up on certain things, right? It has to actually not check certain behaviors. One of the things that it does not check are behaviors that are expected to be very fast, such as putting things on the stack. And so those don't get instrumented by Valgrind. And as a consequence, bugs don't get caught. But the whole point of C++ is that you can actually make things fast and simple at the same time. And so of course we want to write the code this way, and we would expect our tool to deal with it and diagnose the bug. Valgrind is not going to be able to do that. Even with these optimizations in place, Valgrind is simply too slow. All right? Valgrind slows down the execution of your program by 20x, sometimes 30x. That's often an unacceptable slowdown. You may not even finish running your program to observe the bug and get a report from the tool. We need to do better than that. There's a very fundamental way that we can do better than that, and that is to actually do the instrumentation, to do the dynamic analysis through Clang itself. Because Clang is not just a front end, it doesn't just analyze code, it actually generates code. And in generating code, Clang can generate exactly what we need to dynamically check each of these invariants. And by doing it, when we generate the code, we can be much, much more efficient, and we can be more accurate. And this is something that's ongoing in development as part of Clang and LLVM. It's called address sanitizer, which replaces some parts of Valgrind, and the follow-on to that is actually called thread sanitizer, which does data race detection. Now, in the interest of time, I'm not going to go into a lot of details. Also, sadly, I couldn't get the examples for thread sanitizer to work because all of the libraries that work with thread sanitizer don't support threads in C++11. And I was not going to write POSIX threads for this talk. That would just be too. I couldn't get up here and actually project POSIX threads at you guys. Like I would get run off the stage. Rightfully so. Okay. But we can do some things. We can do some things with Clang today. And I at least want to mention those because this is the way in which we want to do dynamic analysis. So here we have a bug that's very similar to a bug we saw earlier where we're actually shifting too far, right? But this one we can't catch statically. There's no static analysis that's going to work. These two functions might be in completely different files. One of them might be shipped to you from a library vendor. There's no way you're going to easily catch this, right? We need something more powerful. Well, we can actually ask Clang to build this with dynamic instrumentation enabled to check for this undefined behavior. Clang has a mode called catch undefined behavior. It will actually add some limited instrumentation to the binary. Very, very lightweight, very low overhead. And when you run it, you'll actually get a crash rather than undefined results, right? It'll crash at the exact point at which undefined behavior would have happened, all right? This is something we're trying to develop in Clang. This is the future, we think, and so I don't want to give the impression that this work is done. There is a tremendous amount of effort to be done in the form of dynamic analysis aided by compilers, because that's what will enable dynamic analysis to be fast and accurate enough to be usable by everyday engineers all the time. For reference, you can take address sanitizer. You can use it to secure Chrome, a web browser. You can load it. You can browse the web interactively. You don't even notice the slowdown. All right? That's the kind of dynamic instrumentation we want because that's what we can use to catch real bugs in pervasive situations. Okay. So let's talk a little bit about C++. We've been talking about these tools, we've been talking about Clang, what we can build with Clang, but I want to bring things back to C++, and in particular I want to bring things back to C++ 11, because that's what we're all here to talk about. And C++ 11, I want to say, is making things much better. I had a bunch of slides in this talk. I was going to show all kinds of crazy slides about all the ways that C++ 11 makes your code less prone to the types of errors I've shown, but unfortunately, or fortunately, Bjarne and Herb have done a much better job of showcasing all of the beautiful things you can now do in C++. I think they literally had a slide for every single example I had up there. So you guys know what you can do now. You have safe memory management, you have safe threads, you have safe concurrency primitives that you can use and you can rely on, and that is what's going to make your code correct and make your code predictable. But we're not done yet. All right, there is more work to be done with C++ 11 to make it really safe, to help defend about it. Herb Sutter started to hint at some of this, and you're going to see some similarities here because I worked closely with Richard Smith, who gave him one of these examples. So you might have written this code initially when you're writing in C++ 11. You might have written this code, and it would work as you would expect. It would do what you would want it to do, but you would have listened to his talk, and you would have heard that you should use auto. There's no reason to be declaring a type here, but unfortunately, by trivially adding auto to this code, you actually make it do something completely insane, all right? Because in fact, when you run this code, it's going to actually assert. And again, you'll notice I was not able to use Clang here. I did want to bring this back to C++ 11, but remember generalized initializer lists? Yeah, that's one of the things that's not done yet. I'm sorry. We're working on it. We're working on it as fast as we can, but that one's not done yet. So this is an interesting thing. We don't have a warning here. Right? We don't have any diagnostics here. We're not catching any of this. But we could. We truly could. We could actually look at how this variable is used. We could look at what type it actually has. And we can see that using auto and brace initialization for this is probably suspect. It's doing something really strange here. It's very unlikely the user actually wanted to create a variable with the standard initializer list type. Especially when we go and look at how it's used later on. It's very unlikely that that was the intent of the programmer. We can detect this and we can warn about it. We need to start building up a body of warnings in Clang targeted at C++ 11. That's the next big thing for making C++ 11 safe. The standards committee has done their job. They've actually tried to craft a language that is as safe as possible, that is predictable as possible, but as we gain field experience, there are two things that are going to happen here. One, we're going to go to the language and we're going to improve it and we're going to fix the bugs in the language. And simultaneously, we need to go to the implementers and we need to ask them to catch these pitfalls for us, to make sure that they are actually looking after us and they're looking after the other engineers learning it. And it's very important. It's very important that as implementers of C++ 11, that we race ahead. That we race ahead and find these pitfalls early and get warnings in place so that as people are learning C++ 11, as we are trying to get adoption of the language, people are not scared away by pitfalls that are easily handled and far more minor than the pitfalls of the slides you've just seen, right? These pitfalls are small and we can fix them. But we need to do it fast so that we can get adoption. Okay, so there are a couple of other interesting pitfalls I want to look at. One of them is regards to decal type. Decal type is really tempting because you don't have to write type names. You shouldn't have to write type names. Unfortunately, there are some expressions that don't work correctly with decal type when you use it in this way. It's not doing what you mean for it to do because this expression does not necessarily have the type you expect. This expression can have the type of a template. That template might be something very surprising. It might be an R-value reference. It might be something else. You don't want to blindly use decal type for certain scenarios because you can't predict what it will do, okay? Similarly, we have cases where we have something that seems very nice originally, but actually is a trap, right? We can use move semantics to avoid wasted copies, but we have to be careful because references are just references, and we can move away local variables, we can leave dangling pointers. It's very easy to make mistakes like this. We need to actually implement warnings for the new ways that these happen with C++ 11. They should be less often, but we still need the compiler's help here because humans aren't going to spot the error, right? We have to have the tools to help us. Finally, and this one is actually the one that scares me. And this one is one that will never happen like day to day. This one's going to happen once in a blue moon. These are the pitfalls that you can't find all of in the language. You simply must catch them in the implementation and tell the user what has happened. What do you think is printed by this program? Any guesses? What do you think? No, come on. What do you think is printed by the program? Oh, let me ask a different question. What do you want to be printed by this program? X. We all want X to be printed by this program. What do you think is actually printed by this program? Well, actually, hold on. It turns out that it is printed. X is printed in the old standard. C++11 changed the semantics of this program. Suddenly, this is no longer going to form an X object. It's no longer going to call that function. It's going to pick an entirely different overload. This expression at the bottom is a null pointer constant. This is a surprising and unfortunate interaction between generalized constant expressions, default initialization rules, and the fact that we must remain compatible with C++98. We have to support the old forms of null pointer constants. When you combine all three of these together, you get this code. Do we expect programmers to write this? No. No one's going to just write this every day. This is not going to be a pervasive problem. But when someone accidentally writes this by some strange happenstance, they're going to lose hours of their day trying to figure out what on earth took place. And they're not going to understand it. We need to catch these types of pitfalls with tooling that can actually tell programmers what has happened and correct it for them. And it's really, really important. This may seem like an edge case, but the time lost when it happens is massive, right? And it shakes confidence in the language. It makes people distrust C++, and there's no reason to do that here, right? This is the ultimate of edge cases. So let's talk about making C++ safer. I would really like to talk about that. I hope you have some good questions for me. And I do also want to mention one thing, and this is a shameless plug. Clang is an open source project. We need patches. And I don't mean patches welcome in the snarky way that a lot of people like to say, haha, patches welcome, we're not doing your work, we're not going to actually maintain this. No. I mean patches are really, really welcome. Clang is unique in that it's an open source compiler that's written in C++, that's a very friendly code base and has a very friendly community. Please, come submit patches to it. We need more people contributing to make this better. Okay, and so if you have any questions about how to contribute to Clang, please come and ask me. And now I think we have a little bit of time for questions. And I think someone would like the very first question.
Could you walk us through the previous example?
Okay.
I didn't quite understand your explanation.
I didn't understand it either. Richard Smith and I worked on this one for a day or two to make sure we think we understand it. We may still be wrong. All right? Just like Howard said, this is a new language. We are all learning about these interactions. So the belief is that S picks up a default constructor here, right? And that default constructor is a valid constant expression because this is an aggregate, right? There's nothing that would make this not viable for use inside of a constant expression. All right, once we do that, we know what the meaning of that default constructor is. The meaning of the default constructor for S is that it zero initializes inside of a constant expression. All right, and so it's important. Now, the next key piece here is that when we construct a temporary S down here, that actually forms a constant expression because we might be trying to call a constant expression function. And then when we pick in out of it, that's still a constant expression because we've made sure that S is nice and simple and fits all of those rules. Again, we might be trying to call a constant expression function. Yes, this is in main, but maybe it's not in main. Maybe it's even in a template function. We might be trying to implement a constant expression here. And so we follow those rules all the way down. Now, at the end of the rabbit's hole, we end up with an integer whose constant value is 0. And there's no distinguishing between this version of an integer value 0 and the literal 0 character written in the source code. And so we must assume that it could be a null pointer constant, and we call f. Now, why didn't this form a null pointer in C++98? Well, we didn't have generalized constant expressions. We didn't have a way to say that we might be calling a constant expression, and so we knew very clearly that default constructing s here had nothing to do with constant expressions, right? That was not even in the picture. And so we also knew that n coming out of it wasn't going to be a constant expression. That wasn't in the picture. It was just the value 0 with a very clear type. And because of that, it was actually able to hit the implicit conversion and actually form x. I'm so sorry.
I have a question. It seems like, besides having a warning about this, which is great, thank you very much.
Sure.
It seems also like we ought to be able to fix this in the standard. It seems like a bug. Have you submitted a defect report?
As I think Richard came up with it Monday, no, we have not submitted a defect report. We will. It isn't clear how to fix this, though, because maybe you have ideas, but it seems tricky. So we'll see.
I have a question for you here. All of the stuff you're mentioning up here sounds absolutely wonderful, and all I can think of is how much it's going to increase my compile times and how it's, especially on the link times. Is there anything we can do, at least especially on the link times, to make this go better? Template link times are one of the reasons that lots of people don't go that way. And as a compiler person, that falls into your court.
Okay.
Thank you.
Okay, so the question is how can we ensure that compile time doesn't decrease? Well, I have a couple of things to say to that one. The one is, I'm very sorry I couldn't actually put this in the slides. A coworker of mine managed to actually get benchmarks of Clang's compile time last night and get me these really nice graphs, and I just did not have time to put them into the slides. I may try and squeeze them in, but let me say that Clang is really, really fast. For slow C++ code, for heavily templated C++ code, Clang is about twice as fast as GCC at compiling your code. All right? And that's a big improvement. 2x is a big number in compile time performance, because people have been looking at this for a while. Link time performance is something different. I think there are a lot of interesting proposals of how we might solve the link time performance issue. Some of the things that I've seen talked about recently include modules, and using modules to actually do more of the linking work ahead of time to make dynamic libraries more rich things that we can kind of link once and ship to your system and you simply refer to. I think that has great promise. I also think that our current linkers are not slow because of how much work we are asking them to do. I think that our current linkers are slow because we haven't yet fully studied the problem of how to link binaries efficiently. And we haven't yet done that study in a radical enough mindset. We often get constrained when we're looking at linking problems by trying to support 20 to 40 years of history. Right? We sometimes get constrained by trying to use the exact same file format and specification that was optimal in 1975. And it's not clear that that remains the case. And so I think that there are a lot of really interesting ways to actually make links dramatically faster. And I mean, orders of magnitude faster simply by re-examining the problem from the ground up and being willing to kind of do a more fresh start approach. There's actually a project that's part of LVM that is trying to write a new linker. I don't know if they're really going to aim to do that the first time around, but I do have some hope we may get some radical ideas that look to improve this. Go ahead, Bjorn.
Just a follow-up. It would have been nice if people would use a null pointer instead of 0 and null, and that would have eliminated that problem.
Yes,
but
it would have.
I have a suggestion. If people write a 0 constant that's not actually called 0 or 1 minus 1 or that one, give a warning.
So that's actually the warning that Richard Smith implemented in Clang because of finding this. And we looked at a large body of code, and it was actually very surprising how frequently this warning fired. We found a large number of places where people were doing this, some of them correctly and dubiously doing this. Other places we found bugs, just rife with bugs. But there actually is correct code that appears to use this to choose non-preprocessor, non-literal names for null. We found a lot of C++ 98 code that used a constant integer k null because it wasn't a preprocessor macro. Dubious, but I don't know how best to fix it. It's likely this warning will end up making it in.
You mentioned that Clang doesn't work on Windows. Could you elaborate on that?
I would love to elaborate on that, especially with this audience. So Clang faces some big challenges with Windows. One of them is, quite frankly, Visual C++ is a really good compiler. That slide, or the several slides of motivating examples that I gave at the beginning, that doesn't apply to most Windows development, and so it's consequentially a lot harder to build a big movement to go and undertake the very, very significant effort of building Windows support into Clang. And that's, I think, actually the primary reason why. A secondary reason why is that as a consequence of the first, the existing Clang community includes very, very few people with any knowledge or expertise about Windows, and so we're woefully unable to support it and unable to build new features in it. There are a small number of people that are working on this because of things like diagnostics and static analysis and some of the potential benefits of that. But there are a small number of people facing a very, very large project, and the rest of the community can't even help them very effectively because it's out of our domain. And so the thing we need to make Windows support in Clang a reality are two things, right? And they're the two things that every open source project I've ever in the world looked at needs. We need patches and we need infrastructure, because there's no one company that's providing the infrastructure for an open source project, and so you need to get it from as many different places as possible, and it turns out that the two companies that try to provide infrastructure are really bad at providing Windows infrastructure. We don't know what we're doing there, and we do a bad job of it, right? And simultaneously, all the people contributing patches don't know what they're doing with Windows patches, and they don't do a great job of it, right? I can't even review Windows patches coming into Clang because I don't know enough about Windows to assess whether they're correct. We need people, and we need infrastructure. If you'd like to help out, we'd love to have you.
Excellent.
Okay, you said that you have now errors, warnings. Are you envision you will have suggestions? So, for example, Clang can suggest that you can use initializer list here, or you can substitute this with algorithm, or you can use auto here, something like that. So it is easier for people to transition to some best practices.
Absolutely. We definitely want to have suggestions. So if you'll note, almost all the diagnostics we show that when appropriate, we have these notes attached to them that give candidate fixes. Now, there's something you have to understand, though, about suggesting fixes. Clang will only actually attach a suggested fix to the diagnostic itself when the diagnostic is an error and when it can actually recover from that error by parsing as if the user wrote what it suggested. Unless we do that, you don't get a suggestion. And the reason is that it's very, very easy to cause suggestions to take the entire program off the rails. There's been a lot of research here. It's easy to run away with suggestions, and so we have a very high bar for suggesting fixes. Warnings are different. Because warnings are not invalid code, we cannot recover parse. We can't reject the program, and so all of our suggested fixes for warnings are attached to notes as options for the user to take, right? But we absolutely need to have options for the user to take for all of the C++11 warnings we come up with. And if we don't, if there's not a best practice that we can suggest immediately when we spot one of these issues, then we have an even bigger problem, right? We can suggest, null pointer here, and that's really important, and we can suggest other things that are really important here. We need to make sure that we have suggestions that are actually best practices and well understood.
Excellent. Thank you, Chandler. Big hand for Chandler.